Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the course Analysis of Variance and Design of Experiments. And you can recall that in the last two lectures we had understood the basics and some results which are related to the vectors and matrix theory that we are possibly going to use in the forthcoming lecture. So now from this lecture we are going to start formally with the topics of analysis of variance. So now first we have to understand what are we really going to do in this lecture and in the next couple of lectures and in this course. You see, when we are talking about analysis of variance, then there are two ways in which we can look at this tool. The first tool is that we try to look at it as if this is only a problem of testing of hypothesis, and we are trying to test a and we are trying to test a hypothesis where we have drawn the sample from different population, different normal population, and those populations are such that their means are different, but their variances are the same. And then we simply want to construct a test for testing the hypothesis for the equality of all the means. So that will be a pure statistical problem, and this type of test can be developed using the likelihood ratio test. The second question is, what is this analysis of variance and why are we doing it? And based on that concept we can employ the principle of least squares to estimate different of parameters in a linear regression model, and somehow we can interconnect the linear regression model and this analysis of variance. And then based on that we can develop a test of hypothesis for conducting the test for the same hypothesis, that is about the equality of means. So the question here is this: what is the relationship between the two types of test of hypothesis that we are going to develop by the principle of likelihood ratio test and using the tools of least squares and linear regression model or linear model. So now what I am going to do here, that the outcome of both the approaches is the same, you are going to get the same result. So first I am trying to consider here the likelihood ratio test, and then later on I will try to develop the same test using the theory of linear models and principle of least square, or say method of maximum likelihood estimation, and then I will try to show you that you are going to get the same outcome. Now once you are convinced that by using any of the approach you are going to get the same outcome, then whenever you want to develop an analysis of variance test, you can use any of the approach. So that is my first objective, that in the forthcoming lecture first I will try to establish that the result that you obtain through the likelihood ratio test and the principle of least square or method of maximum likelihood over the linear model, both are going to be the same. Right. Now the first fundamental question comes here: what is this analysis of variance and what is our objective? Because I personally believe that once the objective in the life is clear, then we enjoy the journey also. So you see, whenever we are trying to conduct an experiment or there is some outcome, The outcome can be from some experiment or some real or say natural process. That outcome is usually dependent upon several variables. So, now the relationship between the input variables and output variables can be non-linear or linear. So, we are going to assume here a linear relationship. Now, the question is that whenever we are trying to see the effect on some output variable, that effect can be caused by more than one variable, and the effect of some of those variables can be significant and the effect of some of the variables may not be significant. Now, the question is this: how to see that which are the variables whose effect is significant and whose effect is not significant. That is the objective that we are trying to fulfill through the tools of analysis of variance. So, as the name suggests, analysis of variance, that means we are trying to analyze the variability in the data that is coming as an outcome of some variable. Now, the variability in the outcome is going to be caused, or that is going to be affected by more than two variables. Now, obviously, in case if I say suppose there are 4 factors or 4 variables which are going to affect the variability of the outcome. Now, suppose out of these 4 there are 3 variables or 3 levels which are very important. So, now my question is this: how do I know that which of the variable is not that important and the remaining 3 variables are really important? So, suppose I know that okay, variable numbers 1, 2 and 3, they are important for us, and suppose 4th is not important. So, now if you try to think what will be the effect of this situation on the total variation on this data. So, these variable 1, 2, 3, 4, we are initially assuming that they are going to affect the outcome, and hence they are going to affect the variability inside the outcome. So, now in case if the variable number 1, 2 and 3 they are more important and variable number 4 is not that important, or in very simple words, the variable number 1, 2 and 3 they are contributing the most in the variability of the data, and variable number 4 is contributing the least in the variability of the data. So, my question is how to identify or how to establish statistically and scientifically that variable number 4 is the variable which is contributing the least in the variability of the data. So, one option is this: if somehow we can partition the total variability that is being contributed by say this 4 variables, that variability due to variable number 1, variability due to variable number 2, variability due to variable number 3 and variability due to variable number 4. And in case if I say that the total contribution of the variable number 4 towards the variability is very small in comparison to other 3 variables, don't you think that we can conclude that the 4th variable is causing the least variability? Hence, it is possible that it is not affecting the variable that much in comparison to the variables number 1, 2 and 3. So, if you try to see what we have done, we have partitioned the total variability in different components, and we are trying to see the magnitude of these individual components, and based on that possibly we can take a final call that whether a particular variable is going to be significant or not. So, now well, these are the things which are convincing to us, but unless and until we do it in a scientific way, in a statistical way, nobody will accept it, nobody will believe on us. So, that is the way we are going to analyze the variance and develop that test of hypothesis, so that we can see that the effect of different variables or their levels on the total variability of the output variable. That is first thing. Second thing is this: in a statistics, this linear model that we had discussed, that is in the form of y equal to x beta plus epsilon. This is a very general model. This model can be used in the linear regression analysis, analysis of variance, as well as analysis of covariance. The model y equal to x beta plus epsilon, where y is the output variable, x is the input variable or its matrix, beta is the parameter, and epsilon is the random error component. Depending on the situation, we can have different types of model. For example, y is already random. The input variables x, that can also be fixed, that can also be random. The parameters beta, that can be fixed, that can be random, or that can be a combination of the both. And based on that, we have different types of model: fixed effect model, random effect model, mixed effect model, etc. And if you try to relate it all of them with the setup of a linear regression model, they can be obtained from the same setup by just making a suitable assumption. So, now in this lecture, my idea is, and my objective is, to introduce you with all these concepts, and we try to understand how we are going to associate different types of model, different types of definitions with the setup of linear model. Right. So, okay. So, with this objective, we begin our lecture. And remember one thing: the lectures which I am going to now take, they will be based on a certain topic, and it might be possible for me that I may not be able to finish the entire topic in a single lecture. So, I will be continuing on, say, more than one lectures on the same topic. So, I will try my best to have a break at a logical point, but in case not, then I would always request you that you please try to attend the second lecture only after understanding the earlier lecture. Okay, so let us begin our lecture. Okay, so now first we try to have a quick revision of this linear model, and this is also called a regression model. And our objective is that we are going to construct a test of hypothesis for a very general setup, and in statistics that is called as general linear hypothesis. Right. So, first we need to understand the background for creating a test of hypothesis for such a general linear hypothesis. Right. So, our objective is this: we are trying to associate everything with respect to the linear model. So, let me first give you the symbols, notation, and the setup of this linear model. Although we had discussed it in the earlier lecture, but then because we were trying to do many results, so every time the symbols and notations were changing depending on the definitions. But now we are going to understand here the linear regression model or the linear model, and we are going to fix our symbols and notations. Right, and I will try my best to use the same symbols and notation in the forthcoming lecture. So, unless and until we try to deviate from this symbols, notation, or their interpretation, we have to follow the same definition throughout the lecture. Okay, so now we say that let y1, y2, yn be a sequence of independent variables associated with the responses. Right. That means, whenever you are trying to conduct an experiment, there are going to be input variable, there are going to be output variable, and the output is affected by one or more than one independent variables, right. So, this y is going to indicate the outcome variable, which is also called as a response variable. So, now this relationship between the response variable and the independent variable here, say x, on which we have obtained the observation, say xij. So, we have essentially the variables, say x1, x2, xp, they are your independent variable that we discussed in the earlier lecture also, right. They are going to affect the outcome here y. So, now we have conducted the experiment and we have given the value x 1 to be like x1 1, x2 to say here x21 and so on here, and then for the pth variable it is the value here is xp1, and based on that we are going to get here the outcome y1. So, we try to write down, and then we are going to have some here error, say here epsilon. So, that is going to take the value here epsilon 1. Now, I can write down the relationship between say here y1 and all the independent variable x1, x2, xp as here like this: beta 1 x11 plus beta 2 x 21 plus up to here beta p xp1 and plus here epsilon 1. And in case if you try to take its expectation, and if we assume that the expected value of epsilon 1 is equal to 0, then this relationship can be written here like this one, right. And the similar relationship can be written for y1, y2, yn. So, this entire relationship can be expressed in the form of expectations, that expected value of yi is equal to summation j goes from 1 to p beta j xij, where I goes from 1 to n and j goes from here 1 to p, right. So, this is actually the linear model in the expectation form, right, and here we assume that variance of yi is sigma square. That means, all the observation y1, y2, yn, they have got the same variance sigma square. Well, in case if this variance also varies, then we have a different type of problem, and the variances are the same, then we call is that they are homoscedastic variances, and if there are different, then we call them as a heteroscedastic disturbances. That means, the variance of epsilons or the variance of yi's, this is not going to be the same. But anyway, we are not going to consider that condition over here, but we are simply going to assume that all the values of yi have got the same variance sigma square. Now, in this setup that we know, this beta 1, beta 2, beta p, they are the unknown parameters, and here this xij is what you have written here, they are the known values of the independent variables, or they are also called as covariates. That is another name of these independent variable, and these variables or the this covariates are indicated by x1, x2, capital Xp. So, we have got here p covariates, right. And in case if you want to write down the same thing in the form by introducing here a random error component, then we can write the same model here as say yi is equal to j goes from 1 to p beta j xij plus epsilon I goes from 1 to n, j goes from 1 to p, where this epsilon i's are this IID, that is identically and independently distributed random error component, and we assume that each of this epsilon I has got mean 0 and variance sigma square. So, we can write down here that expected value of epsilon I is 0, variance of epsilon I is sigma square, and the covariance between epsilon and epsilon j is equal to 0 for I not equal to j, right. So, in this case you can see here that this is another form of the same model that we have considered here. right. The only difference is that in this case you are trying to introduce here a random error component, and this random error component is trying to take care of all the factors which are going to affect yi, and somehow we are unable to take care of them, right. Because if I say, for example, when you are trying to conduct an experiment in a field, and suppose you want to see what are the variables or those factors they are going to affect the yield of a crop. So, now even if you try to see the moisture level in the entire field, that you try to assume to have some value, but that is not going to be the constant at all the places, right. Even if you try to give the certain quantity of fertilizer to a field, then the amount of fertilizer that has been absorbed at a given place in the field, that is going to vary. Well, this variation may be a little bit different, or that may this variation may not be very much high, but still the values are not expected to be exactly the same, right. Beside those things, there will be couple of variables which we are unable to handle, we cannot take care. So, their effect or their joint effect, that is being assumed that it is going to be indicated by this random error component epsilon i's, right. So, now we have got here a model in these two formats. Now, these two formats can also be expressed in the form of a vectors and matrices, right. So, in the form of vectors and matrices, we had considered earlier the setup of say linear equation, and we had tried to convert them or to express them in the form of a vector and matrix. So, the same thing is going to use here, that you try to write down here this equation for all the y1, y2, yn, like this one here, and then you try to club all the values in the y or say x, and then you try to club them in the form of a vector and matrix. So, in matrix notation, the same linear model can be expressed as y equal to x beta plus epsilon, where y is the n cross 1 vector of the observation, say y1, y2, yn on the response variable, and this matrix here x, this is a n cross p matrix. You can see here there are 1, 2 up to here n rows, and then here 1, 2, 3 up to here p columns, right. So, this is indicating that you have got here p independent covariates x1, x2, xp, like as here x1, x2, and here xp, and then you are trying to collect a number of observation on each of this independent variable. So, all those observations have been clubbed together, they have been written in the form of an n cross p matrix, which is indicated by here capital X, right. So, this capital X is going to be n cross p matrix of n observations on each of the p independent variables x1, x2, xp, and this here beta, this is a p cross 1 vector of the regression coefficients beta 1, beta 2, beta p, right. So, they are the unknown parameters, and this beta I is associated with x I, because you can see here in this model here, if you try to write down this term over here summation beta j x I j, you will see here that this model is going to be like here y is equal to something plus here beta I x I plus and so on. So, we call it that beta I is the parameter which is associated with x I. So, that is our simple terminology by which we try to address this fact. And then epsilon is also n cross 1 vector of the terms epsilon 1, epsilon 2, epsilon n. So, this is a n cross 1 vector of the random errors, or that is also called as disturbances in the language of linear models. And we simply assume here that expected value of epsilon is equal to 0, and the covariance matrix of epsilon, which is here like this, expected value of epsilon prime, that is going to be sigma square I p, and we assume that here rank of x is going to be p, because you have seen that if you try to employ here the least square estimation, then the ordinary least square estimator that you obtained earlier in the lecture was x transpose x whole inverse x transpose y. If you remember, we had obtained it like this. So, now in this case what is happening, that in case if you want to compute this value, the value of beta hat, then you have to assume that x has got a rank p. So, that the inverse x transpose x whole inverse can be found. So, you can see here whatever assumptions we are going to make, they are going to be useful in the analysis at a later stage, right. Now, when we are trying to look at this model y equal to x beta plus epsilon, right. This model is sometime called as linear model, sometime linear regression model, and sometime this is also called as analysis of variance model or linear model for the analysis of variance. So, first thing here is, what is the difference between a regression model and this linear model for the analysis of variance? That is going to be used in the design of experiment. So, first we try to understand how the values of x and beta are going to be there in the analysis of variance case, and how do we address them. So, when we are trying to consider the setup of analysis of variance and we are trying to consider the design of experiments, then this matrix here x, what we have called as n cross p matrix of the observations on the p independent variable, that is called as design matrix. And there is a reason why this is called as design matrix, because once you will try to learn the topic of design of experiment, so you will see there whenever you are trying to conduct an experiment, you are trying to give different values or different suitable values to these independent variables, and they are the values which are in your control, and you try to assign them values suitably, so that you can obtain the outcome in a proper way, in a correct way, in an efficient way, right. So, that is why, since this matrix is corresponding to the designing of the experiment in which you are trying to assign these values which are going to be used in the experiments, that is why this is called as design matrix, right. And this beta 1, beta 2, beta p, they are the parameters, they are called as effects. And these independent variables or covariates x 1, x 2, x p, in the case of analysis of variance, they are actually the counter variables or indicator variables. So, do you know what is the meaning of counter variables or indicator variables? So, indicator variables are those variables which takes value at some point that are going to indicate the absence or presence of some characteristic. For example, if I say, suppose a student can be a male or that can be a female, right. So, now I can define here a variable, say here x, say gender, that can take value here 1 if a student is male, and it takes value 0 if the student is female. And similarly, if somebody likes say tea, coffee or cold drink, then these options can be indicated by a variable, say a taste equal to 1. If the person chooses tea, it takes value 2. If the person chooses coffee, and it takes value 3 if the person chooses cold drink. So, these values here in this case 0 or 1 or say 1, 2, 3 in the case of taste, they are simply going to indicate the absence or presence of the effect. Well, in case if you say that okay, taste equal to 1 means tea and taste equal to 2 means coffee, it does not mean that is the twice of 1, that means the coffee is the twice of tea. No, that is only the indicating that what the person is liking or what is the choice of the respondent, right. Whereas, when you are trying to consider the same model in the setup of linear regression analysis, then this is going to be different. There the variables are going to be like different variables like which are continuous, like as height, age, weight, etc. So, that I will try to discuss in the forthcoming slide, but at this moment you have to understand that in the case of analysis of variance model, these covariates, they are called as counter variable or indicator variable. Actually, they are counter variable or indicator variable, and their values, say here xij, this counts the number of times the effect bj occurs in the ith observation xi. Right. So, here you will see that in the context of design of experiment and this analysis of variance, this xij will mostly takes the values 0 or 1, but it is not a mandatory rule. Xij can take any value, but in case if I try to choose that 0 or 1, then the calculation and the interpretation of the results become simpler. That is the only reason that people try to indicate the values of xij by 0 and 1. For example, in case if I say xij takes value 1 if an effect is present and it takes value 0 if the effect is absent. Don't you think that psychologically it is very convincing? Right. So, similarly, in case if I try to take here xij equal to 1, that is going to indicate the presence of an effect beta j in xi. And in case if I try to take here xij equal to 0, the absence of effect beta j in say xi. So, that is how we work in the case of this analysis of variance model. And you have to just remember one thing, that when we are trying to consider the same model y equal to x beta plus epsilon as a linear regression model, then these covariates are usually continuous variable. Right, means they can take any real value. For example, this height means height can be 150 centimeters, this can be 160 centimeter, this can be 150.5 centimeters and so on. Right. So, when all the independent variable and covariates are continuous, then we have the y equal to x beta plus epsilon model as a linear regression model. And now, in case if there is a combination means that some of the independent variable or covariates, they are the counter variable and remaining are the continuous variable, then in that case the same model y equal to x beta plus epsilon, this is called as mixed model. Right. So, the model which we have considered here, right, in this case analysis of variance, that is the setup that we are going to use under the analysis of variance through this linear model. When we are considering all the independent variables to be continuous variable, the same model is going to be called as linear regression model, and we are going to use the setup of regression analysis. And when some of the independent variables are counter variable and remaining are the continuous variable, then the model is called as mixed model, and it is used in the case of analysis of covariance. Right, that we will try to talk about towards the end of the course. Right. Okay. So, now the one question comes over here, that when you are trying to use the same linear regression model y equal to x beta plus epsilon in the case of linear regression analysis and in the analysis of variance, and you will see that you are going to employ the similar type of estimation methodology also. For example, in the case of linear regression analysis, we try to use the principle of least square and method of maximum likelihood to obtain the estimators for the unknown parameters. So, the same thing we are going to do in the case of analysis of variance also. So, now the question is that when we are trying to use the same estimators in both the case, what is the basic difference between the interpretation and the setup of analysis of variance model and linear regression model, right. So, now we are trying to understand the role of linear model in the context of linear regression analysis and analysis of variance, and we try to understand that how these two are going to be different. So, now we try to consider here the multiple linear model like this one, y equal to beta 0 plus x 1 beta 1 plus x 2 beta 2 plus x p beta p plus epsilon. Well, means I am trying to include here an intercept term also, right. And you can see here that what is this intercept term? If you try to take here expected value of here y, this is going to be beta 0, and if you try to take all x 1, x 2, x p to take value here 0, then this is going to be beta 0 plus 0 up to here 0 and plus expected value of epsilon, which is assumed to be 0. So, this beta 0 is going to be expected value of here y, that means this is the average value of y. That means, if you try to put all the independent variables at 0 level or all x 1, x 2, x p takes the value 0, then the average value of y is your intercept term, right. And the use of intercept term in the model, that decision is the choice of the experimenter, and the experimenter has to understand what is the phenomena, and based on that, this decision has to be taken that whether the model will have an intercept term or not. For example, if I say, suppose if I take here one simple example, suppose x 1 here is quantity of fertilizer and x 2 here is say here irrigation, and based on that we try to obtain here an output variable here y as here yield of crop. Now, an experiment is conducted, and when we are trying to give some quantity of fertilizer and some quantity of irrigation, then we are going to get some output, that is the yield of the crop. But now, suppose if I say you do not give any fertilizer and you do not do any additional irrigation, then are you going to get the outcome of the yield to be 0? The answer is no, because the soil also has some fertility, and then there is going to be a rainfall, there is some moisture in the soil. So, that will contribute and there will be some amount of crop in most of the cases. Yes, surely if you are trying to use some fertilizer and some additional irrigation, this crop is going to be more. But my question here is not that. My question is simply, if you do not give any quantity of fertilizer or irrigation, then are you going to be the to get the yield of the crop as 0? Answer is no. So, that means in this case I have to consider here a model, say expected value of y is equal to beta 0 plus the variable, and the model will have an intercept term. But in case if I try to take here one more example, suppose I say that x is the say a current, means electric current, and y here is the say light in the bulb. Now, in case if I say that if there is 0 current in the circuit, then do you think that the bulb will glow? No. And if there is current in the circuit, only then the bulb will glow. Yeah, I am not talking of solar power or other things, right. I am simply talking of electrical bulb. So, now in this case what will happen? In case if my input, that is the value of the current, that is 0, then the output is going to be 0. So, in this case we will not have an intercept term in the model, and we are going to simply consider here a model like y equal to x beta plus random error. So, that is how you have to take a call whether you want to have the intercept term in the model or not. And we also know from the tools of linear regression analysis and linear models that when you have the intercept term in the model and when you do not have the intercept term in the model, the statistical tool, their interpretations and their implementation, they are also different. Well, I am not going into that detail over here. So, my question here is that when you are trying to consider the multiple linear regression model or multiple linear model here, and if you try to consider here the regression model, then all this x1, x2, xp, they are going to have different types of variables, like as x can be, say here quantity of fertilizer and quantity of rainfall, quantity of irrigation, etc. These are different variables. And when we are talking about analysis of variance model, then also we have the same variables, but they are going to be identified by one more characteristic, which are the levels of these variables. How? Let us try to understand it now first. So, in the analysis of variance, you will see that we have one way analysis of variance, two way analysis of variance, three way analysis of variance, and so on. So, or we call it as say analysis of variance in one way classification model, or say analysis of variance in two way classification model, or analysis of variance in three way classification model. So, what is the difference among these models? When we are trying to consider the one way classification model, then there is only one independent variable, there is only one covariate. When we are trying to consider two way analysis of variance, or there is a two way classification model, then there are two independent variables, or there are two covariates. And when we are trying to consider the three way analysis of variance model, or we are trying to consider three way classification model, then there are three covariates or three independent variables. But now the question is, how are you going to differentiate between the regression model and analysis of variance model, because regression model can also have one variable, two variable, three variables, and so on, right. So, when we are trying to consider the analysis of variance model, that is obvious that all the independent variables, they are going to be in the format of an indicator variable. They will be taking value like 0, 1, 2 and so on, right. So, in case if I say that suppose alpha here is the intercept term, well, I am trying to change here the symbols so that I can explain you in a much better way. Otherwise, we have associated the symbols beta for the parameter, but now I am trying to take here three different types of parameters which are indicated by here beta, gamma and delta. Once you understand that thing, after that we are going to use only one symbol beta to indicate my parameters. So, but here I have a different objective, and I feel that I can explain you in a much simpler way if I try to define them by different symbols. Okay, so, suppose this beta, gamma and delta, they are the effects associated with the say three covariates x, z and w, right. So, beta is associated with x, gamma is associated with z and delta is associated with w, and they are all the counter variables x, z and w, because they are now associated with the analysis of variance model. And one thing you have to keep in mind here, that here you can use here that I have used here a name ANOVA, right. This ANOVA means say analysis of variance, that is a very popular name. So, sometime instead of using this analysis of variance term, we also try to use the ANOVA, Right. So, when we are trying to consider the one-way analysis of variance, for which we have to consider the one-way model, the model will be like this one: y is equal to alpha plus x beta plus epsilon. And when we are trying to consider here two-way model, then it is going to be like here this one: y is equal to x beta plus z gamma plus epsilon. So, you can see here, as we had added x beta, similarly we have added here z into gamma. And similarly, if you try to consider the three-way model, then we have here three variables x, z and w, and the three-way model can be written as y is equal to alpha plus x beta plus z gamma plus w delta plus epsilon. So, you can see here that in the one-way model there is only one independent variable. In two-way model there are two independent variables, and in three-way model there are three independent variables. But now one question comes here, that the same thing can happen in the case of linear regression model also. The regression model also can have one independent variable, two independent variable or three independent variable. So, what is the difference between the two? Right. So, in order to understand this thing, let us try to consider an example of an agricultural yield. Suppose the dependent variable or outcome variable or the steady variable is the yield, and the yield of a crop is going to be dependent upon several independent variables, say x1, x2, xp, where for example, this x1, x2, xp are the different variables which are going to indicate different types of effects. So, now we have to just see how this interpretation of x1, x2, xp is going to change when we are trying to consider the same linear model as a linear regression model or as a analysis of variance model. So, when we are trying to consider this x1, x2, xp in a linear regression model, so we have a setup of regression analysis, then this independent variables x1, x2, xp, they are going to be continuous variables like temperature, quantity of fertilizer, amount of irrigation, etc. No issue as you try to conduct a usual experiment. But when you are trying to consider the analysis of variance model, then they are going to have a different type of interpretation. Right, but the mathematical setup will look exactly the same as the setup of a multiple linear model. So, now in case if I say suppose x is my here covariate, and this covariate here is quantity of fertilizer. Now, when you are trying to conduct the experiment, you will try to give different quantities of fertilizer in the field. Right. Suppose if you try to give 1 kilogram of fertilizer in a given area, or another option is this: you can give 2 kilogram of fertilizer, or similarly you can give here p kilogram of fertilizer. So, here the variable is the same, quantity of fertilizer, but the values of the variable that is changing, and that is the main issue here that we have to understand, that when we are trying to give here only 1 kg of fertilizer, that is going to be treated as one covariate, say x1, and when we are trying to consider 2 kilogram of fertilizer, this is going to be considered as, say here, another independent variable indicated by x2. And similarly, if you try to give here p kilogram of the fertilizer, then this is going to be considered as here another independent variable, say, and that is indicated by xp. Right. So, now you can see here once again you have here the variables here x1, x2, xp, but they are going to indicate the values of the covariate. Whereas, when you are trying to consider the linear regression model, in that case this x1, x2, xp, they are going to be different variables, say temperature, rainfall, irrigation, etc. Right. So, now in case if you try to write down this one way model in the setup of a multiple linear model, how are we going to write it? How are we going to express it? That is very important for you to understand. So, now in case if I try to consider the multiple linear model here as say y equal to beta 0 plus beta 1 x 1 plus up to here beta p x p plus epsilon, same model. Now, there is no issue. Now, I am going to define here the variable here x 1 to be like this as a counter variable. Say x 1 will take value 1 if the effect of 1 kg fertilizer is present, and 0 if effect of 1 kg fertilizer is absent. And similarly, if I try to take here x 2, x 2 will take value the 1 if effect of 2 kg fertilizer is present, and this takes value 0 if the effect of 2 kg fertilizer is absent. Right. And similarly, this variable here x p, that is again going to take the same values 1 and 0, but now x p is taking value 1 if the effect of p kg fertilizer is present, and it takes value 0 if effect of p kg fertilizer is absent. So, what are you going to do? That for example, if you have here two plots and suppose here you give 1 kilogram of fertilizer and here you give 2 kilogram of fertilizer, and suppose there are these are the only two choices. So, this is my plot number 1 and this is my here plot number 2. So, for the plot number 1, x 1 will be taking value here 1 and x 2 will be taking here value 0, and in the plot number 2 x 1 will take value 0 because the quantity of fertilizer that is given here, that is 2 kilogram. So, when the value is 2 kilogram, then the value of x 1 is going to be 0 and the value of here x 2 is going to be here 1. So, this is how the observations are going to be assigned when we are trying to conduct the experiment. Okay. And in case if you try to substitute these values in this model, means whatever value you have considered here, if you try to substitute here in this model. So, you can see here that when you are trying to consider the plot number 1 or plot number 2, at a given time you can give here only one choice of quantity of fertilizer. Means in this plot number 1, either you can give 1 kilogram of fertilizer or you can give 2 kilogram of fertilizer. You cannot give 1 kilogram of fertilizer as well as 2 kilogram of fertilizer in the same field, that cannot happen. So, now in case if you try to express this phenomena through this model, so what are you going to do? When you are trying to write down here the observation for the plot number 1, that will, so in this case x 1 is going to take value 1 and x 2 is going to take value 0. And in the case of the output from the second plot, that is going to be indicated by y 2, and in this case x 1 is going to take value 0 and x 2 is going to take value 1. Now, the same thing I am trying to do here, that suppose there are p such labels. So, and suppose in a given plot we have used here only 1 kilogram of fertilizer. So, obviously, in this case the effect of 1 kilogram of fertilizer will be present and the effect of all other quantities of fertilizer 2 kg, 3 kg etc., they will be absent. So, in this case the model can be written here as say y is equal to beta 0 plus beta 1. Now, x 1 here is equal to 1 and all the values of independent variables x 2, x 3, x p, they will become 0. So, I can write down here the model b 2 into x 2 equal to 0. So, that is actually beta 2 into 0 and up to here beta p and with x p equal to 0 plus epsilon. So, you can see here this I can write down here as a beta 0 plus beta 1 plus epsilon, and all other terms associated with beta 2, beta 3, beta p, they are going to be 0. And similarly, if you try to take here another plot where you are trying to use here the 2 kilogram of fertilizer, then what will happen? That you are going to write down the linear regression model here as say like this, beta 0 plus beta 1, but now x 1 will become 0 and beta 2 with x 2 equal to 1, and all other x 3, x 4, x p they will be taking value 0, and so I can write down here as y is equal to beta 0 plus beta 2 plus epsilon. And similarly, if you are trying to use only here p kilogram of fertilizer in this plot, then in that case the model can be written here as a y equal to beta 0 plus beta 1 plus beta 2 plus up to beta p, where the associated variables are all going to be take value 0 except x p equal to 1, and this model can be written here as a y is equal to beta 0 plus beta p plus epsilon and so on. Right. So, you can see here that in this case you can just write this model exactly in the same way, and from here I would simply like to show you here one thing, that finally your this y is going to be here beta 0 plus beta p plus here epsilon. So, this is for x p equal to p. Now, you can see here if you are trying to write down here y is equal to beta 0 plus beta 1 plus epsilon, this is indicating that x 1 equal to here 1 kg is being used, y equal to beta 0 plus beta 2 plus epsilon, this is indicating that x 2 equal to 2 kilogram is used up to here. This the same thing that y equal to beta 0 plus beta p plus epsilon, where we are going to use here the value x p equal to p kg. Right. Okay. So, now let me stop in this lecture here, and you can see here in this lecture I have just given you a basic fundamental, and I have explained you how this analysis of variance model can be expressed using the setup of linear model. And you have the same linear model y equal to beta 0 plus beta 1 x 1 plus beta 2 x 2 plus beta p x p, but the same model can be used in the regression analysis, and the same model can be used in the analysis of variance. And under the analysis of variance you have different types of setups, one way, two way, three way. You might have heard about these names, say one way ANOVA, two way ANOVA, three way ANOVA. So, these are the models which are going to be used in those one way ANOVA, two way ANOVA, three way ANOVA, etc. But there is a big difference that how these variables are going to be interpreted, and this is very basic fundamental in the topic of analysis of variance that you need to understand. Now, after this there comes another question, that whenever you are trying to conduct an experiment, suppose you are trying to conduct the agricultural experiment and you are trying to collect the crop. That means, and suppose you are trying to use the quantity of fertilizer as say 1 kilogram, are you really going to use it only at one place or in the one plot, or you try to use it in different plots? For example, you can use 1 kg of fertilizer in say 5 plots, you can use 2 kg of fertilizer in say 7 plots and so on. So, how are you going to express this thing in the framework of linear model? That I am going to consider in the next lecture. Remember one thing, whenever we are talking of the analysis of variance or design of experiment, it does not mean that we have the examples only from agricultural. Sometimes if you try to read the books, they are always trying to give the examples from the agricultural experiment. Yes, I agree that this topic originated from the agricultural experiment, but these topics whatever I am going to consider here, whatever I am going to handle here, whatever I am going to explain here, they can be used in any science, whether this is medical science, biological science, engineering science, whatever you say I will say yes. So, you try to have a quick look on this lecture, to try to revise it, and I will see you in the next lecture, and I will try to continue with the same topic, same setup. So, please come prepared for that thing with a good revision. So, you try to revise, and I will see you in the next lecture. Till then, goodbye.